Hello and welcome back to Complex Analysis. And as always, first I want to thank all the nice people that support this channel on Steady, via PayPal or by other means. Today in part 8 we will continue talking about the Cauchy-Riemann equations, and I also explain what Wirtinger derivatives are. For this, as often, we consider a complex function f that is holomorphic on an open domain U. And for such a function, we will define a new differential operator as a partial derivative with respect to the variable z. Then, when we apply this to the function f and look at a given point z0, this is often called the Wirtinger derivative. However, this is not quite correct because there's also another Wirtinger derivative. This one is a little bit strange because it's written as the partial derivative with respect to z bar. However, it turns out that both things here are well defined and indeed useful for our theory. For example, for a holomorphic function f, this one here should give us the complex derivative of f at the point z0. With this in mind, we will be able to define this new differential operator. Also, then we will see that for a holomorphic function, the other Wirtinger derivative should be 0. Therefore, let's first concentrate on the Wirtinger derivative on the left hand side, df dz. Now, to make our life a little bit easier, let's write x plus iy instead of the point z0. So this means this is the complex derivative of f at the given point. Hence, it's just another complex number which we can write as a plus ib. And now this is what we have learned in the last videos. The real part and the imaginary part can be written as partial derivatives. This works when we take the real part of the function f as a function u and the imaginary part of f as a function v. And then this a here is du dx and b is dv dx. Of course, both partial derivatives here are to be evaluated at the given point xy. However, in the upcoming calculation, we will omit this point to make everything clearer. Of course, now in the next step here, we want to use the Cauchy-Riemann equations. And in order to include them correctly, the best thing we can do is to double this complex number here. So you see, we add the same number again, but then we have to divide everything by 2. And now the idea is that here in the second part, we apply the Cauchy-Riemann equations. So instead of du dx, we can write dv dy. And on the other hand, dv dx can be written as minus du dy. Okay, what you now should see is that some symmetry is involved. We have two partial derivatives with respect to x and two with respect to y. And this is what we can apply to our knowledge that u is the real part of the function f and v the imaginary part. Or in other words, we can also look at the map that has xy as an input but a complex number as an output. Namely, f at the point x plus iy should be the output. So you see, as the map fr, this carries exactly the same information as the map f. It's just again another point of view. And this helps us because this function we can write as u plus iv. And now you might already see, on the left hand side we use exactly this. Here, the first part we can write as the partial derivative with respect to x of u plus iv. And now in order to get this in the second part as well, you see we have to pull out a minus I. And when we do this, you see we also have the partial derivative now with respect to y of u plus iv. Okay, so this is the result for f prime you really should remember. Indeed, it's easier to remember when we use that u plus iv are essentially the function f. Hence, we can just define two new differential operators. Namely, we just call the first one df dx and the second one df dy. And indeed, this makes sense. This one is the partial derivative with respect to x when you see f as this map here. Okay, soon I show you an example and then these two operations should be clear. However, first I want to define the Wirtinger derivatives because with this calculation here, we already know how to do this. We can just use combinations of the partial derivatives with respect to x and y. Firstly, now when we write d dz, this should stand for 1/2 times dx minus I dy. So you see, this is exactly what we have learned above. The definition makes sense, and for a holomorphic function f, it gives us the complex derivative of f. Okay, now in a similar way, we will define d dz bar. And indeed, this should look very similarly, so we also take 1/2 times and now dx plus I dy. We do this because you see, by the Cauchy-Riemann equations, we get 0 when we apply this operation to a holomorphic function f. And here please recall, this fits to our motivation from the beginning. Okay, then as promised, let's look at an example. It shouldn't be a complicated one, so let's look at a polynomial. Namely, we just look at the quadratic function z². Which means, using x and y, we have x plus iy squared. Hence, let's just expand the square, which means we have x squared minus y squared plus I times 2 times xy. Therefore, this first part here is our function u, and this part is our function v. With this, we can immediately calculate df dx, which is here 2 times x plus I 2y. And similarly, we can calculate df dy, which is here minus 2y plus I 2x. Now, both things can be simplified when we just use the fact that x plus iy is the complex number z. Hence, df dx is simply 2 times z. And in a similar way, you see for df dy, we have 2 times I times z. So we can always use that I squared is minus 1. Now, with these two nice short expressions, we should be able to calculate the two Wirtinger derivatives. So let's start with the second one, df dz bar. It's 1/2 2 times z plus I times 2iz. Again, we know I squared is minus 1, so we get 0 here. This is what we expected, because the polynomial is a holomorphic function. Okay, then in the next step, it's not hard to calculate df dz. It's the same calculation as before, but now with a minus sign here. Therefore, in this case, in the parentheses, we have 2z plus 2z divided by 1/2 gives us back 2z. Also here, the result is not so surprising, because it should give us the complex derivative of f. Okay, then I would say, let's summarize the video by stating the important fact we have proven here. Indeed, this is something one can nicely remember. Namely, a complex function f defined on an open domain U is holomorphic if and only if df dz bar is equal to 0 at all points. Indeed, this equivalence you already know, because here we simply have hidden the Cauchy-Riemann equations. And then, in this case, as we have proven above, the other Wirtinger derivative gives us the complex derivative of f. So f prime can be calculated by using df dz. Okay, with this you now know a lot of different differential operators we can use in complex analysis. Then I hope that I see you in the next video where we will talk about power series. Have a nice day. Bye.